We talked about something in reactions before called substrate scope. That is, what do the starting materials need to be? We said for the Suzuki reaction, you need a vinyl or aryl boronic acid or ester. Last time we focused on aryl halides as the other coupling partner, but it turns out that vinyl halides are okay too. So another example of a Suzuki reaction that works would be, say, this vinyl halide and let's say this boronic ester, and we're just going to be generic about what those alcohol groups are. And of course, again, remember the way that you're going to recognize the Suzuki reaction, the difference between the Suzuki reaction and the Heck reaction is the Suzuki reaction, the palladium catalyst source is palladium 0. You also need, let's see, for the Suzuki reaction, usually some kind of base. In the text, it's usually hydroxide. In the lab, you can use any number of things, but we'll stick with the text examples. And remember, the Suzuki reaction couples the carbon that has the halide to the carbon that has the boronic acid, and stereochemistry is preserved. So if it's E here and E here, the new bond goes in the exact place of the bonds that were broken. In blue is the new bond, and there we go. Okay, so you can use the Suzuki reaction to make 1,3-dienes to make the bond between the two alkenes. And notice that the stereochemistry is the same over here. So it's called a Suzuki cross-coupling reaction because you're literally Legoing the two pieces together. Okay? I don't think you're going to face this on the final, but there are tons of things that you can do with dienes, like Diels-Alder reactions, and so you can see how the Suzuki reaction can be quite useful. Okay, we're going to do some more practice examples, but before that, I want to finish covering the Heck reaction and some of the others. Let's see. So, since Monday, I've had some questions about what exactly is the mechanism of this transmetallation reaction. Notice in the transmetallation step of the mechanism, we lose Br. It leaves the metal as Br minus. It leaves as Br minus because it's an X-type ligand. And in place, we install the pink group from the boron onto the metal. How does that process happen? It's actually, this reaction sort of outside my immediate area of expertise. I don't have a lot of experience with it experimentally in the lab. And what research I did suggests that this step, actually the mechanism is not really well characterized. So there isn't really good arrow pushing for this step. This reflects a limitation that we have in science, which is if a step in a mechanism is not the rate determining step or is not before the rate determining step, sometimes we have a hard time studying it. The rate determining step for the Suzuki reaction is known, I just don't know what it is. So you've reached the limits of my expertise, and obviously I'm not going to ask you questions that go beyond that. All right, well, let's look at the Heck reaction in greater detail. The substrate scope for the Heck reaction is slightly different from the Suzuki reaction. You do need an aryl or a vinyl halide, so that's the same as the Suzuki reaction. The difference is on the other side, you don't need any particular functional group other than an alkene. So you might think, why would anybody ever do the Suzuki reaction if instead you could do the Heck reaction and you don't need a boronic ester on the other side? Isn't that better? And the answer is, I'll show you one thing, that a stereochemical issue that makes a difference, which is an explanation for why you do the Suzuki reaction. Other factors are more practical and you'd get if you were doing the reactions in the lab and had a lot of synthetic experience, but they're not really important for us here. The way you can tell a Heck reaction from a Suzuki reaction is that the starting material, or rather the palladium source that you put into the reaction, is palladium 2 instead of palladium 0. Why did they choose that? I don't know. You're going to be frustrated even more because it turns out that the palladium-2 that you start with is not the active catalyst. This is another feature of a lot of different kinds of catalytic reactions. Sometimes the metal complex that you put in is not actually the thing that does the catalysis. Instead, something happens to the metal first, it changes its bonding structure, and then it becomes an active catalyst. This is an example of that. Though you put in a source of palladium-2, the thing that does the catalysis you will see is palladium-0. It is known how this palladium-2 source becomes palladium-0. I'm not going to show you because it's not worth our time. If you want to know, come talk to me. I'll be happy to show it. I just looked it up on the internet and wrote it in my notes, but it's not really worth a lot of our time now. Notice that in the Heck reaction, the two carbons that are coupled are the carbon in blue, where the halide was, and one of the two carbons of the alkene. I've shown it here as though it is the terminal carbon of the alkene. It doesn't have to be. So the carbon that gets coupled could be, it's not necessarily always the less substituted side of the alkene. Most of the time it will be. You may encounter situations where it isn't. You should just be prepared for both. Obviously, in a predict the products question, I'm going to keep it pretty simple, pretty similar to what is shown here. But if you encounter some weirdness, it can be good to have in the back of your mind. Think about what would happen if the bond was made with the other carbon of the alkene. Usually this Z group is an electron withdrawing group, but it can also be an alkyl group. It just sort of depends. And the key difference, do you remember how the Suzuki reaction had stereochemistry over here on the boronic ester, and that stereochemistry is preserved in the product? Not so with the Heck reaction. There is no stereochemistry for this terminal alkene, but the new bond goes in such a way that it is selective for trans on the side that was the original alkene. So we did an example where I showed you, say, two Heck starting materials over here. The vinyl halide was E, and it's still, that double bond is still E in the product. There was no stereochemistry over here for the alkene, and it's selective for E. Okay, so it's specific on the side of the alkyl halide, it doesn't change. It's selective for the E stereoisomer on the side of the alkene. So you can see that over here, if we change the alkene starting material, or rather the vinyl halide starting material, to Z stereochemistry, we get same Z stereochemistry in the product, but again, we're selective for E on the side of the alkene. All right, yes?
If E space is already filled on your alkene, will you get a Z product or just no reaction?
If the E space is already filled on the alkene, will you get a Z product or no other reaction? It will turn out that even if there was a substituent here, there's an intermediate in which the double bond is gone, and you can rotate around that bond. You'll see that as I show you the mechanism. Yeah. So no, it's selective for the Z stereochemistry. Okay. What else? Yeah.
Will the reaction still work if there's a substitute on that side of the
Will the reaction still work if it's substituted on this side? I don't know, actually. It's a good question, and I don't have a great answer for that unless we get to some examples in the problems from the text. But I think if you look at the Heck problems for the text, for most of them, you're dealing with simpler situations with simpler alkenes. Okay. Good. Let's show you the mechanism for the Heck reaction. I think I kind of messed up because I think I'm taking notes on last time's notes, which is a bad idea. So we'll just create new notes and paste a page. All right, paste. That's good enough. Here we go. Okay, so let's show you the mechanism. And again, we'll do it for, say, this general reaction. So I'll copy that. We'll just scroll down. Okay, so we'll start with a catalytic cycle, kind of like we've done earlier. Remember that one of our starting materials was this aryl halide. Could have been a vinyl halide. The metal is palladium. And as I said, we're not going to worry about how you get from palladium 2 down to palladium 0. This is thought to be the active complex. It's actually the metal catalyst is actually pretty similar for the Heck reaction versus the Suzuki reaction. So if we were to do what we've done previously, we're not going to slow down to do this. The overall charge on this complex is neutral. Otherwise, I would have had to show it. Those are two L-type ligands, so this is a source of palladium 0. In the first step, you've got an oxidative addition of the phenyl bromide bond to the metal. Now remember, conceptually what happens in oxidative addition, though no transition metal or inorganic chemist or organometallic chemist would do this, is we take 2 electrons from palladium, we form a new bond with the carbon of the benzene ring that's bonded to the bromine, and then we take the 2 electrons from the carbon-bromine bond and we make a new palladium-bromine bond. Or the other way around, you can't tell. I've tried to make that point multiple times, so hopefully you're comfortable with that. The product now has palladium with 2 sigma bonds, 2 new sigma bonds, one to bromo, one to the phenyl group, and understand that of those 4 electrons involved in the 2 sigma bonds, 2 came from the metal and 2 came from the carbon halide bond. Overall, the charge is still neutral, but palladium is now in its +2 oxidation state. You can tell that's the case because now palladium has 2 X-type ligands, the phenyl and the bromo. And it's a D8 electron. And a D8 electron metal, you can count the total number of electrons. It's 16 electrons total. Okay, let's see. Before it was a D10 with 14 electrons total. All right, now the fact that this is a 16 electron complex is important because at this stage we have a step that's called ligand binding. And this is really kind of interesting. The pi electrons on the alkene act as an L-type ligand, meaning we're going to get a weird complex, and L-type ligands where pi bonds are bonded, pi electrons are bonded to the metal, are somewhat difficult to draw. And I'll try to represent them as best we can. Here are the 2 X-type ligands and the 2 L-type ligands. It's thought that the pi electrons adopt a somewhat axial above the metal position, and we're going to use a dotted line to indicate that the pi electrons from the alkene are bonding to the metal. It's 3 atoms really involved in a 2 electron bond, the 2 carbons of the alkene and then the palladium, and these electrons come from the L-type ligand, the alkene. So now palladium is still in its +2 oxidation state. It's still got 8 d electrons, but now it's an 18 electron complex, and there we can't bind anything else. We are what's called coordinatively saturated. Okay. Now, I don't expect you to be able to predict what's going to happen next. I'm simply showing you what the steps for the Heck reaction mechanism are. I'm really not going to push you too much on these mechanistic steps aside from the concepts of oxidative addition and reductive elimination. What we're going to do next is a new mechanistic step that may not make a whole lot of sense, but it's important to see how the reaction happens. That's called migratory insertion. And what happens in migratory insertion is that the bond, the carbon phenyl group bond, is going to migrate and insert itself into this carbon, in between this carbon and the palladium, and then the pi bond between the two carbons of the alkene is going to become a new sigma bond involving, we'll call this carbon A and this carbon B. So maybe I'll use different colors for A and B. So in red, we get the bond with carbon A, and in blue, we get the bond with carbon B. Okay, so what we make after that now still has the bromo attached to the palladium, still has the phosphine ligand, and has this new, which I'm going to draw in blue, bond with carbon B of what used to be the alkene. I'm going to now draw both Z and H groups. On carbon A, we should have the new bond with the phenyl group, and then, of course, 2 hydrogens. Okay? If you're following along with palladium oxidation state, palladium is still palladium-2. You still have 2 X-type ligands. It's still a D8 metal. But now we're back down to a 16 electron complex. And the reason for that is we took these 2 carbon palladium bond electrons and we made a new carbon-carbon bond. Okay? So check, I mean, if you're looking at what we're trying to do in the Heck reaction, we're trying to make a new carbon-carbon bond, that one right there. We just did that. Mission has been accomplished, but if you've seen, we've lost the pi bond. We got to get the pi bond back. Okay, what will happen next is, I think we're going to need just a little bit more space here, so I'm going to move things like this. What happens next is a step that's called beta hydride elimination. It's going to look a little bit like an NADH style oxidation. And this is the step that is selective for the trans alkene. So first, we don't have time to redraw things, but can you see that this carbon A in red has 2 hydrogens attached? Okay. And can you see that the bond between A and B is a sigma bond, so we can rotate around that bond? Okay. Now, imagine that we showed dashes and wedges appropriately. There would be a way to draw this molecule, rotate around this bond, such that the phenyl group was as far away as possible from this Z group, right? We're not doing that here. I mean, actually, with the magic of erasing, we can. Sort of cheating. But notice that those 2 carbons are not actually stereocenters, so there should be a way to rotate in such a way that the phenyl group and the Z group are maximally apart from each other, while one of the protons on carbon A is close to the metal. So there's a sterics, that sterics explains this step. You want to have the Z group and on the carbon B and the phenyl group on carbon A as far apart as possible. Then what happens next is the electrons from the palladium carbon B bond will kick down and form a new pi bond, and hydride will leave, but it's not just floating off as H minus, as we did with NAD plus style oxidations. The hydride is going to get delivered to the metal. The metal is going to accept the hydride. At that point, we lose product. So I'm going to draw the product here in the middle of our cycle because I run out of space elsewhere. If you look, the fact that the Z group on the alkene was opposite to the phenyl group This is the product that we get. That's the new bond that we made. And if you compare the product above, in the example above, this is the thing that we just made. Okay? What we've still got attached to the metal, though, is not our starting complex. What you've got is hydrogen and bromine, both attached to the palladium complex. Again, still palladium 2, 2 X-type ligands, 2 L-type ligands, a D18 complex, still 16 electrons total. In order to get to the final product, we need to do a reductive elimination step. And it's thought that what happens in this reductive elimination step, in the Heck reaction, I guess backing up a little bit, one of the things you need for the reaction to work is a little bit of triethylamine, and I didn't add that as one of the reagents in the Heck reaction. You'll see it in your text, I just didn't put it above. The reason for that triethylamine is because at this stage, triethylamine helps with the reductive elimination. It deprotonates the hydrogen, and those 2 electrons from the palladium-hydrogen bond go back onto the palladium. And at the same time, bromide leaves. And that's going to give you, leaving the catalytic cycle, the conjugate base, the conjugate acid of triethylamine, this triethyl ammonium, and then Br minus salt. That then gets you back down to palladium 0 and opens up plenty of space for another turn of the catalytic cycle. So it's fine for you to just, I wanted to show that to you because this is a chemistry class at BYU, and if I don't tell it to you, likely none of you are ever going to see it again. If you forget all of this stuff, you're probably fine in your life, honestly, if you forget this catalytic cycle. What I do want you to recognize is the oxidation states of the metal all the way around, and you're going to need to know which steps are oxidative addition versus reductive elimination. This stuff about migratory insertion and beta hydride elimination, if you were going to walk up to Dr. Michaelis and say, hey, I want to work in your lab, and you already know what these things are, that'll impress him, okay? But if you weren't going to do these reactions in the future, it's possible that you wouldn't necessarily need to know those things. That being said, I do want you to be able to predict the products and provide reagents for the Heck reaction, all right? Yes?
So I just noticed in your cycle, you sometimes it's phosphorus with phenol, sometimes it's hard. I think you can use both, right?
Right. There are many types of phosphine ligands. Often in the Suzuki reaction, it was often triphenylphosphine. In the case of the Heck reaction, it's that, which I didn't want to draw or abbreviate with the O-tollyl, because that's a lot of letters to write so many times, so I just use R.
Okay. So that would usually be that.
It would usually be a benzene ring of some kind attached to the phosphorus. But there are hundreds, perhaps thousands of phosphine ligands that people have tried. Okay, others? Yeah.
Do you want us to know oxidative addition and reductive
Reductive elimination. Yeah, I want you to be able to recognize that. If you're good at counting metal oxidation states, that's going to be easy. Okay, others? Okay, so let's practice a little bit with some sort of predict products. You'll see that, and maybe a little bit of retrosynthesis, you'll see that I got to get out my Geyser glasses, because these, I call them my Geyser glasses. These are actually my grandpa or my grandma, I couldn't tell which, reading glasses. We've been going through their stuff since they both died in October, and my eyes are getting old, and so I scooped up a bunch of reading glasses, because anyway, so these are literally my grandpa's reading glasses. His up-close vision was worse than mine, but there we go. Showing you a couple examples of Suzuki and Heck reactions, just thinking predict products, provide reagents. So let's do a couple of these. Let's start with maybe the Heck reaction. Dun, dun, dun. Oh, this one's fun. Should we do this one? Yeah, you're not looking at it. So this is 28.28. This is a horrific and horrendous molecule. And it's going to involve making a ring, which I know is your favorite thing. Okay, so there you go. Take a look at that. And then intramolecular Heck reaction. And let's just write down the reagents. What the intramolecular Heck, right? You'll need the phosphine ligand, the orthotolyl phosphine ligand, and you'll need triethylamine. When you know, so if they didn't tell you that this was a Heck reaction, you would have to look at those reagents. Whoa, it does not work to look at all of you through the Geyser glasses. You would have to look at those reagents and recognize them as Heck reagents. So that's one thing, that may be memorization that you need to do. Second, you would need to remember, what does the Heck reaction do? Well, it connects a vinyl or aryl halide on one side with an alkene carbon on the other side. And for the most part, unless there's no other choice, you're going to be thinking about that carbon that has an electron withdrawing group on that side. Okay? So we literally just want to make a new bond between those two carbons. We said that the stereochemistry over here, which is E, is going to be preserved. It's going to stay the same. When we make a new bond over here, we said that the stereochemistry is going to be selective for E. Okay? So how do you put these together? It's not as difficult as you think. All you got to do is put an R group there, and then another R group there. Then bring them together, and remember that the new bond goes in here between the blue carbon and the pink carbon. And the new bond goes to the carbon that had the iodide. So we're just going to slide that over. That's then our new compound. Now, you got to figure out a way to draw the rest of the molecule. So, for example, now we're just going to count carbons. From this group, 1, 2, 3, 4, 5, 6, 7, 8, 9 to the ester. By the time we get to the ester, you've got 1, 2, 3, 4, and 5 spaces there to the alkyl halide. So I'm counting like 15 atoms. So just start drawing zigzags and hope for the best. This is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 is the ester, then the oxygen, and the oxygen is 5, 4, 3, let's go the other way. 1, 2, 3, 4, 5. Now that's ugly, and that's probably not the way it's drawn in your text. They probably drew it prettier, but that's the right answer. We just need to get the stereochemistry right at carbon 4. How are we going to do this? Well, up here, carbon 4 has a wedge methyl group when 4 is at a peak with 3 on the right and 5 on the left. There's 4. over in our drawing below, if we tilt our heads, 3 is still on the right, 4 is still on the, 5 is still on the left, and 4 is still at a peak. So boom, and we're done. Doesn't matter that it doesn't look pretty if it's got the right connectivity. Okay, so this is a classic example of being given so much information and worrying and trying to take it all in, focus in on what's important. The decision tree funnel that we went down is, oh look, those are Heck reagents. Now I got to look for the vinyl iodide or vinyl halide and the alkene. Having found those, click them together in the right way with the right stereochemistry, then worry about the rest of the molecule. Are there questions about how we did that? Okay, well, maybe let's do another one. This is one that periodically people show up in my office asking about. Maybe these last two that we'll do are sort of retro-synthetic questions. So I'm going to abbreviate this question. And just say in the book, it said that you can make this molecule from at least the boronic, you make the boronic ester using a hydroboration approach like we talked about last time, where hydroboration works like this. It's a syn addition of the boron reagent across one of the pi bonds of the alkyne to give the following molecule. The hydrogen and the boron are delivered to the same side of the alkyne. Your text says that this one works using this as one of the Suzuki starting materials, this one not so much. Some of you have been confused by that, but maybe now that you see it, you're not so confused anymore. Why can't I make this from this? It's a cis-trans issue, right? Suzuki reaction preserves the stereochemistry of both the the vinyl halide or aryl halide starting material and the stereochemistry of the boronic ester. This method of making the boronic ester can only ever give you E stereochemistry, because as you learned in 351, hydroboration is a syn addition. So you can go ahead and make this one, or you could even make one where it was Z on one side and E on the other. Right? Let's just identify the bond that you would make in the Suzuki reaction. It's that one between the two sp3 carbons. And the real issue is, if one of my partners has to be this one, I'm okay there. I'm okay here because at least one of my double bonds can be E, but here I'm not okay. Does that make sense? Okay. Let's do some retrosynthesis from the Heck reaction. I'm going to draw, and again, once you work on this just a little bit, it's going to become pretty easy. There's not a lot of other options. Let's do this via the Heck reaction, where one of the starting materials is this molecule, which happens to be called styrene. And the question is, what is the other one? So to do this, you need to remember that the Heck reaction works on an alkene and then a vinyl or aryl halide. So you'd have to realize that the styrene checks off the alkene, so your other reactive partner needs to be a vinyl halide. Then go back and remember what the Heck reaction does in making a bond between the terminal carbon of the alkene, and then you've now just identified the bond that was made in the Heck reaction this must be the carbon that had the halide on it. So at that point, answering the question is as easy as drawing that section with the blue carbon and then putting a halide here. Br would be okay, iodide would be okay. Generally, these reactions work better for iodides than bromides because the carbon-iodide bond is weaker than the carbon-bromide bond. They generally work better for bromides than chlorides because the carbon-bromide bond is weaker than the carbon-chlorine bond. Okay, questions there? Yeah? Do you absolutely need a withdrawing group for the Heck reaction? Must not need one terribly, because a benzene ring is not a terribly good electron withdrawing group. So the Heck reaction will work even if you don't have a strongly electron withdrawing group. The main requirement is an alkene. Yeah?
So if we I'm just thinking about the mechanism of the Heck reaction and how the alkene nestles up to the palladium, kind of making a bond.
Yeah.
So in my head, if you have an electron withdrawing group, it would have a harder time doing that.
Right. What is the effect of the electron withdrawing group in allowing the alkene to bind the metal and perhaps facilitating this reaction? To really answer that question, we would sort of need to know some things about transition states and where charge builds up in the transition state. If this electron withdrawing group were an absolute requirement, you might predict that in the transition state there was a buildup of negative charge on the adjacent carbon where it could sort of be stabilized by resonance. That information is probably known for the Heck reaction, I just don't know it. Okay. Well, there are so many more things in this chapter. I have pages of notes more to do. What we were not getting from me in chapter 28 involves a fun reaction of making cute little cyclopropane rings. So, sorry. Aw. And you're also not getting an awesome Nobel Prize winning reaction called olefin metathesis. And that's a shame because that's a reaction we've actually done in my lab for some interesting purposes, which I will have to not tell you about. So I think there you guys have had enough. I think we are done. So good luck on the final. Merry Christmas. Please stay in touch. And thank you all so much. What an amazing gift. I'm just overwhelmed. I can't. This is my overwhelmed face, by the way. Let me try again. Thank you all.